Hi, everyone. Welcome to Distributed Consensus with Raft, or can John describe a PhD thesis in 20 minutes or less? Let's find out. So I'm John Feminella. I've got a website there. There's also a Twitter account that I tweet from. If you would reply to the tweet I just posted with any questions you have, I'd be more than happy to get back to you after the talk is done. Cool, let's talk about consensus and why it's hard. So imagine you have a single node, a place that you could store a value in, and you would like to store a value there. And now you have some client, an agent that's responsible for making requests that store values, and you want to put a value into the node. Later, you'd like to be able to read a value, and you want that value to be the same one that you put into it, right? Because otherwise, if you can put one value in and get a different value out, what's the point of storing that? So if we have a system that does that, that seems pretty easy, right? If we can put something somewhere and then get the same value out that we put in, then we seem to have a system that conforms to expected behavior. What happens when there's more than one party that has to agree on that value? That's the problem of distributed consensus. So when there's more than one party that has to come to a value, or come to an agreement about that value, you have a consensus problem. And distributed consensus is difficult because there's a lot of different ways to try to come to agreement, and not all of them work, or they give up some properties in exchange for others, and there's many different implementation challenges. But they all fall into two kinds of big buckets. The first bucket is called symmetric consensus, where any member of the, any server or any node that's participating in the consensus group is allowed to respond to requests. Asymmetric consensus is where a leader or a set of leaders from among the participating members is allowed to respond to requests. So only certain members are allowed to respond. You can think of this like two people agreeing to go to lunch. So imagine you have Alice and Bob. Alice asks Bob over email, hey, you want to go to lunch at 12:30? And Bob says, that sounds great. Now, Alice and Bob are in a locality bubble. They're close together. Their messages are quick to be sent and quick to be received. So you can imagine that this is not maybe going to lunch, but any kind of message that two people might want to exchange: where to go for lunch, what time we should go to Vegas, when is that report due, any kind of agreement that you need to come to between two parties. So what happens if two parties are far apart? So what happens if Alice and Bob aren't right next to each other, but they're some distance away? Well, then when Alice sends the message, it might take a while for Bob to get back to her. And that's a problem, because if it takes a while, what happens if Bob doesn't respond? Well, Alice can't tell the difference between Bob not responding and Bob just hasn't responded yet, right? Those two situations are indistinguishable. So for Alice to know that Bob has a problem responding, we can see that Bob has a problem responding because we're above the level of Alice and Bob, and we can see the entire system. But from Alice's perspective inside that bubble, she can't know that. There's a lot of different, that's not the only way that distributed systems can fail, right? But two of the most problematic are fail-stop failures. That's like what we just saw, where Bob doesn't respond, Bob goes away. And Byzantine failures, where Bob is allowed to respond with any message, not just no message. So Bob could respond with a harmful message, a message that's deliberately wrong, a message that tells Alice to self-destruct, et cetera, et cetera. So this is clearly not a great state of affairs when we live in a really hostile distributed systems environment. So how do we cope with that environment? And the answer of how do we cope is maybe exemplified by something called the two generals problem. This is a classic academic problem that's been studied in great detail. So the two generals problem works like this. There are two generals, which we'll call A and B, and they want to attack a city. And they need to coordinate their attack, or else the city will repel them. So the city is capable of repelling one, but not both of the generals. And the generals coordinate their attacks by agreeing on a time that they will attack. And they do this by one general sends a message to the other saying, I'm going to attack at time T. You should also attack at time T. And I'm going to wait for your acknowledgement so that we can be sure that we're both going to attack at the same time. And if they can do that successfully, they will destroy the city, which is their objective. Now, the problem is that the city has spies and can intercept the messages that the generals are sending. So if it can do that, then it can block or alter or fabricate any message it wants. But for purposes of this, we'll just say that it can only block the message. So it can't transform the message into something else, but it can stop the messages from being sent. And if it can do that, then we can prove that it's actually impossible to guarantee success. So and that's because the other party can never confirm the receipt of the first message. So Alice sends a message to Bob saying, hey, attack at this time. Bob sends a response, but that response might get intercepted. So Bob wants to wait for a response, but now Bob is in exactly the same position that Alice was a second ago, so there's no way for them to come to a 100% guaranteed agreement. So this is just one way in which distributed systems are really difficult. And there are some existing solutions to try to have systems come to an agreement about values. One you may have heard of is called blockchains, and cryptocurrencies use this as a strategy. The problem with blockchains for things like a database is that it's really slow. You have to do a lot of work you're basically doing very hard math problems all the time, and most of your work is spent doing the math problems, not on exchanging messages. The other kind of approach that's been popular is something called Paxos, which is a precursor to Raft, which we'll talk about in a second. Paxos is a very difficult algorithm to implement. It's notorious for having bugs in the implementations, even though it's provably correct. So if you implement Paxos correctly, you do get a distributed consensus system, but it's really hard to implement correctly, so it has lots of subtle bugs in typical implementations and so on. So with Raft was kind of a successor to Paxos in that we tried to make an algorithm that was more easily explainable, and that's what I want to try to do now. The goal of Raft is to have an available, replicated state machine. So available means that if you have a Raft system, you get meaningful responses from some log in the system. So if you give non-meaningful responses that like HTTP 500 or whatever, that is not an available system. So we want to be as available as possible. We also want it to be replicated. We want other nodes in the system to be aware of the log that's the shared idea of what the state of the system is. And we want to have a state machine with each node in the system such that if we receive a list of commands in our log, executing the exact same command should produce the exact same result. So there's a state machine understanding of what's happening in the system. So here's what a typical Raft system might look like. First, it's asymmetric, so the candidates in a Raft system elect a leader who will speak on their behalf. And there are 3 states for nodes in a Raft system. One is being the leader, one is being a candidate, and one is being a follower. Everybody starts in a follower state. So if you boot up your Raft cluster and it's got 5 nodes, then you have 5 followers to start with. After some amount of time, each node contains a randomized timeout value. And when that timeout value expires, the follower becomes a candidate, and it starts a process that's called election. We'll talk about that in a second. If the candidate gets enough votes from the other members of the cluster, it becomes a leader. And enough votes means you have a majority of the nodes in the cluster. If you don't get enough votes before you time out again, then you start a new election and you keep trying to do this until somebody wins. If you are the leader, you could step down to become a better leader if you discover that somebody else is actually in a better state than you are. So if you're the leader but you're not the best leader that you could be told to step down. So Raft divides the view of the world of time into terms. A term is an integer value. It starts at 0 and is then incremented over time, depending on every time you hold an election, you increment the term. So each term starts with an election, and during the election, you're trying to figure out who the leader is. Once you figure out the leader, you can start exchanging messages. You're available at that point. So once you have a leader, your cluster is available. If a leader dies, somebody yanks the cord out of the wall of their server or whatever, not a problem. Eventually, one of the nodes will time out first, and a new election will happen, and it'll elect a new leader in the cluster. So if the election takes too long, don't worry. You can increment the term again, and you'll hold a new election. And then at that point, you'll have normal operation. Then you repeat this process indefinitely. What we hope is that the green bars are much, much longer than the red bars, right? We don't want to be spending our time doing elections. We want to be spending our time exchanging messages, arriving at consensus for people making requests to us. Here's how an election works. Election has 3 steps. You increment your current term, you vote for yourself, and then you ask for votes from everyone else. And we want some properties to be true in elections. So first, we want there to be at most 1 winner per term. We don't want to have an election and then have 5 people win the election. We want 1 winner out of that election. So if we have enough votes from the majority, so in this situation, if there are 5 nodes in our cluster and 3 of the nodes have voted for A, then we know that A must be the winner, even though we haven't received votes from the other 2 members of the cluster yet. And we also want someone to eventually win. So no matter how many elections we have, we want it to be true that if we do enough elections, with some probability, we should know that someone will win. And we do that by selecting an election timeout that is much larger than the amount of time we think it should take to send messages between nodes in a cluster. So if it takes, say, 5 milliseconds to send a message, you don't want your election timeout to be 3 milliseconds, because you'll never be able to send a message before you time out. So you want your timeout to be much larger than the amount of time it takes to send messages between things in the cluster. So typically that looks like 100 milliseconds, 200 milliseconds. Only 3 possibilities in an election. You receive the majority, so you become the leader. You receive a valid heartbeat from another leader that says, hey, I'm the leader, you should become a follower. Or the election times out and you start a new election. So if you receive the majority, then you become a leader and you tell everyone else. If you receive a valid heartbeat, then you go back to being a follower. Or if the election times out, you keep being a candidate and you start a new election by incrementing your term. So let's see what a straightforward election would look like. So here's a Raft cluster with 5 nodes, S1, S2, S3, S4, and S5. And the gray ring around each node tells you what the election timeout is, and you'll see that gradually start decrementing. You'll notice that S2 is about to become a candidate. It asks for votes, and it becomes the leader. So now it's told all the other members of a cluster, hey, I'm the leader. You should increment your terms so that you're up to date with me, and you should keep track of what I say now because I'm the leader. So what happens if we have some problems with our cluster? Can we still have an election? So let's say we've got a situation here where S4 and S3 are disabled, so they've been yanked out of the wall, and we only have 3 members alive in our 5-member cluster. So still enough to get a majority, but some of our nodes are unavailable. So let's see what happens in this case. Notice that S2 and S1 have election timeouts that are very close to each other, so it's possible they might both try to start an election at the same time. Let's see what happens. So S2 starts an election, S1 starts an election at the same time, and they both don't get 3 votes out of the 5 votes, so neither of them can become the leader. So we'll restart, pick a new election timeout. S2 times out first. This time, it's able to get all 3 votes and becomes the leader. So S3 is now the leader, or S2 is now the leader, and we're back in normal operation. So that's just deciding who the leader is. What happens when we want to exchange information? So that's the log replication part of Raft. So a log in Raft just looks like a piece of data that's got an index. An index is the number of log items you already have before this one. So if you've seen 6 items, then your index will be 6. It has a piece of data that represents the thing that you're storing, and then it has the term that piece of data is associated with. So if you receive the data in term 4, that piece of data will have a term 4 attached to it. So a given server's log is a list of these log entries. And a collection of logs for the entire cluster just looks like a list of logs. In this case, server 0 is the leader, and it has 1 entry that the other 2 servers don't yet have. We consider an entry committed if it's on a majority of the servers. So in this case, all the entries except for the entry in position 4 that server 0 has is committed. So everything else is committed, but the entry in position 4 for server 0 is not. Whenever the leader wants to send new entries to the other servers, it does that by including the previous entry's term and index. So here it's saying, hey, I want to send you this piece of data that I have, but before I send that to you, I'm going to also send you a piece of data that says, here's what comes right before this one, so that you can check that you're not only getting the new piece of data, but that you have everything that came before. So you're not missing pieces of data, in other words. So we also want logs to be safe. So we want, if we commit something and we know it's committed, then we want that to be persistent for all the future leaders in the cluster as well. So the leader's job is to propagate those logs to its followers. So here's a case where, there we go. So here's a case where the leader has some entries in its log, and it's going to propagate those entries one at a time to the other followers. Notice that every time it does that, it resets the election timeout because that counts as a heartbeat. So it's telling the other members of a cluster, hey, I'm still here. Here's the last entry that you need to update your stuff with. Also notice, let me rewind a little bit. Also notice that the dotted lines represent entries that the leader isn't sure are committed yet. So here the leader knows that this first entry is committed because it's stored on a majority of servers and it's gotten responses and confirmations that that's been stored. But it doesn't know about the rest of them until everybody's up to date. So once everybody's up to date, all of these dotted lines will fill in, and now every member of the cluster knows that it's only dealing with committed records at that point. So there's a problem, though, because we don't want to vote for someone accidentally who might be a worse leader than we are. So we only want to vote for people that are, we only want to vote for people that we're sure would be better leaders than we would be if we were a candidate. So here's what that looks like. In this case, we've got our 5-node cluster again. S5 just timed out. It's starting an election for term 4. S1 has some records. So if you look at the logs, S1 is the best possible leader right now. But S5 happened to time out. So S5 shouldn't be able to get votes from S1, and it shouldn't be able to get votes from S3 because both of those have better logs than it does. And it's still possible that S5 could become a leader because it could get a majority here. We'll see what happens when that happens. So let's see what happens when this situation occurs. So S5 is about to start a new election. And so S5 did not win the election because it only got 2 out of the 3 votes, and S1's heartbeat to S2 got there first, and S2 decided not to vote for S5. So then it's just a normal election situation where one of them will time out, and then this guy is now a leader, and it will tell everyone to update all their records. Notice that when it told everyone to update their records, it's going to overwrite the entries in S3 because they're not committed, and they're not as good as its entries from term 3. So an entry that's not committed can be overwritten. So how do you decide if you should vote for someone else? So you don't vote if you get a request to vote, you don't vote if your term is better than the candidate's term. So if you're on term 6 and you get a request to vote from someone who's on term 5, you don't vote for them because your term is better. You also don't vote for them if your term is the same as theirs, but your index is better than the candidate's. So if you have 5 records and they have 3 and you're both on term 95, you're not going to vote for them because your index is better than their index. So in this case, S0 cannot get votes from S1 or S2 because its term is worse, right? It's on, if an election starts for term 4, let's say, it doesn't have entries there yet, so it's never going to vote for, 1 or 2. And similarly, S1 can't get votes from S2 because its index is worse. It's missing entries that S2 has. So the last piece of this puzzle is that there is commitment issues in certain edge cases. The first big edge case is what happens if server 0 is the leader right now, and if server 2 became the leader for term 5, entries in S1, this entry could be overwritten if server 2 becomes the leader, right? Because it would propagate its, server 1 would vote for server 2 would vote for itself, now it's got a majority, and server 2 would propagate requests to overwrite entry 3, even though entry 3 is committed. That's a big problem. We thought something was committed and it got overwritten. So that's bad. All those entries that we thought were committed, it could go away and die. So we need a new rule, which is we only consider it committed if first it's majority stored, like we said before, but we also need to add a new piece that says there's at least one entry from our current term that's also majority stored. So in this case, we're going to consider these committed because they're stored on a majority of servers, but we're also considering them committed because we have at least one entry from term 4 of a leader's current term, which is also majority stored. So that's everything we need to make distributed consensus with Raft. Takeaways. First, the fact that I could explain this in a roughly 20-minute talk is something you can't really say for Paxos. I mean, if you look at the If you look at the paper for Paxos, I think it would take you 20 minutes to read the table of contents, much less explain it or try to implement it. Second is that you get really strong guarantees from what is a relatively small set of relatively simple rules about how to exchange information and how to share information among members of a cluster. And third is that you're probably already using it. If you use Cloud Foundry or Kubernetes or Docker Swarm, you're using a technology called etcd, which is a key value store. And the way that etcd shares information with other members of an etcd cluster is, you guessed it, Raft. So if you're using these technologies, you're actually already using an implementation of Raft. So that's everything I have to say. If you have questions, I'd love to be able to answer them on the tweet that I posted before. Thanks very much for having me, and have a great afternoon.